Next section is the minor loss. For the stress by the major loss from previous section can be calculated by use the friction factor obtained from either Moody chart or the above equation, Collie-Brooks equation, adding additional components like valves, bench, T, and the lines add to the overall head loss of the system we call the minor loss. The head loss, for example, is if this figure is show a valve, the minor loss from the valve. The purpose of the valve is to regulate the flow rate by changing the geometry of the system. And with the valve closed or open, there is a resistance to the flow. You can see that this is the flow to the valve. There is the changing of geometry of the flow. And head loss for the pressure drop is specified by using the loss coefficient KL. Okay, KL based on this equation. Okay, and we can write the head loss for the minor loss equal to KL time velocity head. Okay, and for KL is the function of the geometry or the Reynolds number. Okay, that is the minor loss is an equation is it write different meaning. For the many practical application of the Reynolds number is large enough so that the flow through the component is dominated by the inertia effects. So loss coefficient is a function of the geometry only. So KL is a function of the geometry only. And we want to change the minor loss to the major loss using the equivalent lengths. We can use this between the major loss and minor loss. We can show that equivalent length equal to KLD over F. Okay, we can convert from minor to major with the same head loss using this method. A fluid flow from a reservoir into the pipe through a shaft entrance region as shown in the below figure. We expect that there is the vena contracta region may be resolved because of the fluid cannot turn a sharp right angle corner. Okay, to reduce the entrance loss we have to round the entrance region as shown in the figure to reduce the vena contracta effect. Okay, you can see that the flow, if this one is vena contracta effect of the flow because of it's a sharp entrance. We smooth the like this, smooth the entrance, so and the vena contracta is gone. And for flow pattern and pressure distribution at the shaft edge entrance, we expect that there is a loss on this region. And this for if we increase the radius over the diameter for the entrance, we will keep the radius increase with the smaller KL. Okay. But for the exit flow, there is no effects for different re-entrant or shaft or slightly round and well round. So it's K is about to 1. Okay, no loss for the exit flow. And this for the loss coefficient K for the sudden contraction. So once we increase the different ratio of the area, so we decrease the KL. And this one for the loss coefficient for the sudden expansion. Okay, if we increase the ratio, so we decrease the KL. And this table for the show loss coefficient for the pi component, different pi component for the elbow and for the bench T, okay, and union. Okay, different. We can use this for calculate to find the KL loss coefficient for each pi component, and it's the same for the entrance, different K for the different entrance, and it's for the expansion and contraction is for the elbow, okay, and for the T, and this for the valve, okay. And this figure show not only the K but they show the loss in equivalent lengths of the pi. So is alpha is K, but beta is the equivalent length coefficient. In this case is alpha is a K,